Yes, professors, all my dear friends and all participants. My name is Shurajit Bhattacharjee. I am a junior research fellow here at IIT ISM in the Department of Petroleum Engineering. And today I'll be hosting this session, inaugural session for the GIAN course. This course undertakes the task of understanding the imperative need to innovate and collaborate and to meet the challenges of energy demand that our world is currently running through by the means of enhanced oil recovery. The main focuses of this course will be in the unconventional domain, like tight and shale reservoirs, and sustainable practices, regulatory compliances, balances between the environmental concerns and development. Without further ado, I would like to invite our inaugural speaker. She is a veteran of the field and has been awarded in many senses. She hails from premier institutes like Jadavpur University and has a PhD from the Notre Dame University as well. She is the head of the Department of the Petroleum Engineering Department in IIT ISM Dhanbad, Professor K. Kaocha.
Good evening, Professor Sheng, and good morning to all other participants. It's all to this GIAN program with the objective to make the global academic network, to enhance the global academic network. So first, it's my privilege to introduce the Department of Petroleum Engineering at Indian Institute of Technology, Indian School of Mines, Dhanbad. It was started, the institute itself has been started long back in 1926. So this year we are celebrating our centenary program. And our department has been started in 1957 with the need to train the manpower in oil and gas industry. So since then, we are been in the oil and gas industry, training, graduating in a number of petroleum engineering students who are reigning globally in academy as well as industry. So Department of Petroleum Engineering at Dhanbad aims to become the global leader in contemporary as well as the dynamic and evolving energy sector through excellent teaching and research. Our curriculum seamlessly integrates robust theoretical knowledge with practical and hands-on training with the objective to educate our students to excel in emerging technology. Not only the students, our faculty members also focuses in various conventional and unconventional E&P technologies, starting from conventional reservoir characterization, enhanced oil recovery, hydrogen, geothermal, shale, and CBM, and other areas, contemporary areas. So this course, GN course, that aims to have insight into, to provide insight into the EOR techniques used in shale and tight reservoirs. Though in India we have very less shale and tight reservoirs, but we are striving for the best to fulfill our energy security because of low conventional resources in India. So I hope this course will be educating our participants in the special enhanced oil recovery technology in shale and tight reservoirs. So I wish all the best to all the participants for the best learning, and thank you everyone for participating in this. Thank you very much.
Thank you very much, ma'am. Now our speaker was Professor Shukham Rajan, but unfortunately he won't be able to join us for this session. So I'd like to invite our next speaker. He has been a veteran of the field and has hailed from one of the premier colleges of India, IIT Kharagpur. He has been in this in the departments of enhanced oil recovery and oil and gas for more than 20 years now. He has been the former head of the Department of Petroleum Engineering in IIT ISM Dhanbad. Please take the stage, Professor Ajay Mandal.
Good morning, all the participants, and good evening Professor James Singh, and I am really happy that you kindly accepted our request to participate or to take part in this collaborative program. Now, our local coordinator, Professor Sukaranjan Samadar, is unable to attend this meeting due to some personal reason. So on behalf of our local coordinator, I have a brief highlight about the this GAIN program. The Global Initiative and Academic Networks, that is the GAIN, is a program of the Ministry of Education, Government of India. It is designed to tap the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the institutes of higher education in India as to augment the country's existing academic resources, accelerate the pace of quality reform, and elevate the India's scientific and technological capacity to the global excellence. Now, the certain objectives of this program is to increase the footfalls of reputed international faculty in the Indian academic institutes, provide opportunity to our faculty to learn and share knowledge and teaching skill in cutting edge areas, to provide opportunity to our students to seek knowledge and experience from reputed international faculty, to create avenue of possible collaborative research with international faculty, to increase participation and presence of international students in the academic institutes, the opportunity for the students of different institutes and universities to interact and learn subjects in the niche area through collaborative learning process. Provide the opportunity for the technical persons from Indian industry to improve understanding and update their knowledge in the relevant areas. Motivate the best international experts in the world to work on problems related to India. Develop high quality course materials in niche area, both through video and print, that can be used by a large body of the students and teachers. To document and develop the pedagogic methods in emerging topics of national and international interest. Now, for this participant, I want to say something that I request you to attend the class in time. The timetable of the classes of the different classes is already shared. And at the end of the day, the video of the class will be shared to the participants. And as I have mentioned, that it is a certified course, and towards the end of the course, you have to sit for some evaluation process. So I request all these participants to get the details about the classes that will be delivered by our expert, particularly Professor James Singh. Now it is my great privilege to introduce our speaker, particularly the foreign speaker, Professor James Singh. Dr. James Singh is a professor in the Petroleum Department of Texas Tech University. He's a US Fulbright scholar and a distinguished SP member. He had worked in the oil industry for more than 10 years before entering into the academia. His main research areas are enhanced oil recovery, new energy development, and CO2 sequestration. The half and puff gas injection and tight shale reservoirs he proposed has been widely accepted as the feasible EOR method. He holds his PhD degree from University of Alberta. He has co-authored over 300 papers and holds 8 US patents and has published 3 books, out of which the book entitled Enhanced Oil Recovery in the Shale and Tight Reservoirs is very much relevant to this course. He received 2 SP Regional Technical Awards in the year 2013 and 15. Most influential faculty members in the year 2015 and 17, the Outstanding Technical Editor Award in 2005, and Outstanding Associate Editor Award 2008 for SPREE. He was also an associate editor of prestigious Journal of Petroleum Science and Engineering during 2008 to 2011. So thank you. Now I hand over to our
Once
anchor.
again, welcome Professor Jamshen to this course.
Well, thank you, Dr. Oja and Dr. Amanda. And it's my I'm honored to be invited for this program, and I really appreciate the help for the Dr. Mandel's arrangement. He has spent a lot of time and effort for this program. So again, thank you, and thank you for all the course participants for your interest in my course or in this program. Actually, this program has several instructors. So thank you for your interest.
Okay, I want to share that this particular program is going on in online mode. So we have around 20 to 25 participants. They have physically joined in this room, and there are so many participants they have joined in the online mode. So I request you now the start, that is the session 1, that is the lecture 1. So it is up to you, Professor Singh, and once again welcome and welcome all the participants for this GAN course.
Okay, so thank you again, Dr. Amanda and Dr. Oja. So now I'm going to share my. I should start this first lecture, right?
Yes.
Okay, I'm going to let's see, share my screen. Where is it?
You can move this side.
On this side.
Okay, can you see my screen now?
Yes. It's visible.
Okay, that's good. All right. Let me make it a bigger one. All right, so I have already. So first thing, I was starting from fundamentals, very basic, because I was told most of the course participants are the undergraduate students. So therefore, I was starting from a very basic concept. So first, I was starting from the porosity. So first, let's look at this picture. It is a core plug, so it's a rock. So from by look at this rock, so you cannot see any holes, just like a piece of solid, right? So then, if you look at zoom it, make so look at a small area and zoom it. So you can see that this right-hand side is this kind of picture here. You have white represents greens, and this blue represent epoxy. It's kind of liquid. So now you can see from the left, you can see you only have see the solid, but right you can see some epoxy inside. So this epoxy is a liquid. So therefore, you must before this epoxy enter the this room, this inside of the rock, you must have some holes or open space in the rock. So this open space we call pore volume. That's called pores. Okay. So then let's look at a further about this microscope, like not microscope. Let's further look at the structure of the rock and pore. First, this white area represents pores. Okay, here, like this, for example, this area is interconnected pores. So that because the white area is connected, so then the pores are interconnected. But some areas like here, there's there's dead end. So this side you have pores, and the top side, so you do not is closed. So this is called dead end. So in other words, this some pores are beside the dead end. And let's look at the lower left-hand side. You can see that some pores here, the white area represents the pore space. So now this pore space is isolated by these rocks in different directions. So therefore, this pore is called isolated pores. So then let's look at a specific pores. So pore, you have this is the wide area, but here you have narrow area. This is called a pore slit. So then from this picture you can see if the pore is this is how whether fluid can flow through this pore, mainly dominated or determined by how large this pore slit could be. So therefore, when we talk about a pore slit is very important. So next one is we're going to introduce the porosity. Okay, it's called porosity. What is porosity definition? First, we talk about total pore volume divided by total bulk volume. So that is the definition of porosity. And then for the total pore volume, we have an interconnected pore and dead end pores and isolated pore, as we see as we saw earlier, right? So then, so we have different pores. Then we could define different porosities. So first one is called effective. What is effective porosity? So effective means so this pore volume are effective to store fluids. So therefore, this effective porosity will be defined by the volume of interconnected pore volume, dead end pore volume, divided by bulk volume. It does not include the isolated pore volume because isolated so fluid or like for example oil in the isolated pores cannot be produced, right? Because it's isolated by solid rock. So that is definition of effective porosity. Then correspondingly, and it is another one is called ineffective. So ineffective is defined by isolated pore volume divided by total bulk volume. So now you can see if the ineffective porosity and plus effective porosity should equal to the total porosity. Right. Next one, we're going to talk about shale. So what is shale? So because this course, this course we talk about EOR, or enhanced oil recovery in shale and tight reservoirs, right? So then what is shale? So shale is first is fine grain. So that is solid grains are very small. It's a very fine grade sedimentary rock, and typically shale rock is typically deposited in a very slow moving water, and very often found in lakes and lagoonal deposit, or in river deltas. So, or on floodplains or offshore, so beach sands. In other words, basically in low energy deposited in low energy environment. So why do we have to say low in energy environment? So if the low energy energy environment, so that big sand will not be carried over here. So it will be before reach the deposition area, it has been already deposited. So only small sand can be carried over to the deposition area. So that's why we say the shale. Well, that's why we could get a very small grains. And shale is characterized by bricks along thin lamina. So in other words, you see this shale, if you see it from a side, you can see many layers, because it takes many years to deposit the shale rocks. So then different time different sands will brought in the deposition area. So that's why, like for example, this is one sand, like in the beginning, is sand, let's say sand 1. Now after very long time, you have another source of sand to bring, which had road here. Then can keep going on. So you have different sands which had been brought here. So that's why you can see the different layers, okay? And another thing is, by such kind of description, you can see the probability is very small, okay? Before this slide, I should introduce what is the probability? So what is probability? Simply, probability is ability of a rock for fluid to flow. So in other words, like say, for example, in the water, if it's easy for water to flow through this rock, we say this rock's probability is high, otherwise will be low. So shale, this flow ability will be low. So it sometimes is actual low. So therefore, sometimes we call the shale is actual low probability rock. So that is from so let's further look at the structures of shale rock. Right in the left-hand side, so now this scale is about 1 centimeters. So it's so large scale. So this rock is about 2.5 inches, about 2 to 3 centimeters diameter. So now you can say it is solid, right? It's a solid rock. So, but then if you look at a small, this yellow area, like say we look at this rectangular yellow and zoom it, okay? Now in this one, you can see some white area. So it's a white area. It's kind of, some is dark white and the rest is dark. So you can see now, so it's inside you have some pores, some slot, some like small fractures. And then let's further zoom it, make it using it's called scanning electronic microscope is SEM. It's kind of like a microscope, right? So then you further zoom it, you can see in the inside, you have this white area, you have minerals like the quartz, for example, and you have a little bit darker area, it's called organic matter. I'm going to talk a little bit more about what is organic matter. So then it's dark areas have small dark, some dark points for a dark area, and it is pore. Okay, so now you can see in the inside of this rock, we can see some pores, and we can see the solid minerals. But then in shale, we introduce another material called organic matter. So earlier we talked about porosity. When we define the porosity, we define the pore volume and the solid volume, right? But now in the shale, we have another one is called organic matter. This organic matter is, I will talk about later on. It's solid, but if it is heated, it can be converted to the like hydrocarbon, oil, or gas. Okay. So you generally, we mentioned earlier, the shale porosity is very small. And then also we could see the small porosity. What is porosity, typical porosity value? It's about a few percent, probably like say 5% or most of them are less than 10%. So you can, in other words, the total pore volume is about 10%, is only 10% of the total bulk volume. So that's porosity. We also mentioned permeability is very small. Okay, now let's look further and look at the structure. First, let's look at this upper left corner. So you can see now, this is, here you have some dark green or blue area. So we called second pores, secondary pores. So now we have introduced another terminology called secondary pore. So then if you talk about secondary, we must have a primary pore, right? So just a few minutes ago, when I introduced the porosity, we talked about pore volume. That pore volume is formed by deposition of sand grains. So that is called primary pores. But then what is secondary? Secondary means after. So what is this after? Then because of some chemical reactions or some other events, because other events occurred, so you have more pores was formed. These pores are called secondary, or in other words, the pores formed after the rock was formed. Right? So here you have some slides. So these slides are later on, or sometimes we call them microfractures. Okay, and then move to the next one, picture B. So you can see, it's more clearly see here is kind of slot, and some white area is it's mirrors. It can zoom the pictures. And let's look at picture C. So this is, you can have some slots, you have second pores, or sometimes we call this second pore called VAG, right? So now what you can see, for the pores, it's easy to understand we have pore volume, we call it porosity, right? But then from this picture, you can see we have some kind of slot and some big pores. So therefore then, this shale rocks, we could have different type of pore spaces. One is primary pores, we have secondary pores, or sometimes we have slot or microfractures. Okay. Now, next one, I'm going to talk about more about the permeability. I mentioned permeability a little bit earlier, but now let's let's formally or conclusive. Let's formally discuss what is the probability. Let's look at this core plug. For this core plug, and we inject, for example, let's inject water at a Q, and pressure drop is from P1 to P2. So we have pressure drop from P1 to P2, and for Darcy, the French civil engineer did some experiment, such kind of experiment, and he found this flow rate is proportional to pressure drop, which is easy to understand, right? It's easy to understand. As this pressure drop is increased, then flow rate will be increased. And then he also observed if this flow area is larger, then this rate will be higher. And then if this distance core length is longer for specific or fixed delta P, then this longer than Q will be lower. Okay, he observed this relationship to establish equation. He put a K. Okay, K is kind of constant. All right. So then from our common sense, we can understand if the fluid viscosity, okay, fluid viscosity is high, that means more viscous. So then it will be more difficult to flow, right? So flow rate will be lower. So therefore, then we, instead of using such kind of uppercase K, then we use the K, small k over mu to replace this K. So therefore, at the end, we have such kind of equation. And this equation is called the Darcy equation. Now, in this equation, we have small k. So what is small k then? This small k we call probability. Okay. So what is probability then? So formal definition is K is the ability of fluids to flow through a rock. All right. So that's now we have introduced the probability. Then from this description, what we can understand, to put K for shear rock will be very low. Okay. And this rock, this probability, sometimes we call absolute probability. Later on, we're going to talk about what is relative. When is absolute, then we must have another word called relative. So we're going to talk about a relative probability later on. But what is first? Let's be clear. Let's be clear. What is absolute probability? Absolute probability is it's a single phase fluid of a mixed viscosity such is single phase, for example, water or oil, and the saturated flow. So all the pores is occupied by the fluid, or laminated flow. Laminated flow means we can simply understand it like flow velocity is slow. Okay, so that is a condition. So this here are typical probability values. Now we mentioned for shear reservoir, it's about nano-Darcy to micro-Darcy. So then what is you need to get an idea of what does it mean by nano-Darcy, or get a sense of nano-Darcy or micro-Darcy. Then let's compare the oil reservoir, conventional oil reservoir. It could be about 200 or even thousands millidarcy. So now what you can see here is about 1,000 times or even more than 1,000 times smaller for shear reservoirs. Okay, so gas reservoir is about 20 to 200, and pore reservoir is about a few millidarcy. So that's the idea. Now you get some sense what is the value about what is the value of probabilities for the rocks. Okay, And then in the earlier, I mentioned shale rocks has the primary pores, secondary pores, and some slot. So now, so like some is big pores, right? So here we call, sometimes we call box, and the solid rocks we call matrix. And some slot we call fracture, or to be different from the hydraulic fracture I'm going to mention later on. So this fracture maybe we should call mini fracture. That means small fractures. All right. So now this is the real description of a rock. Then you can, from this real rock, you can see this box, matrix, or fractures are randomly distributed. Randomly distributed. So different rocks have different arrangement, different distributions. How do we describe such kind of model? If we want to, it's very complex, right? So it's random. It's random. So it's complex. So to be easy to describe such kind of medial or porous medial, sometimes we use such kind of right-hand side model. This is, in this model, we just simply use such kind of regularly packed rock. You have a matrix, and then between the matrix, we have fractures. Okay, we have fractures. So in the matrix, we have primary pores. Okay, then is other vagues, mini fractures volume will be described by these fractures. So in other words, we convert this real rock by converting into such kind of ideal mathematical model. Mathematical model. We call this model, dual porosity model, because it has fracture, which is kind of secondary pores, and we also have primary pores. So then you have two types of pores. So therefore, we call this model is a dual porosity model. Okay. So then in the later on when we talk about a simulation, you understand what you need to recall what kind of model we are dealing with. Okay. Now, next I'm going to introduce another concept or another parameter for shale rock. So which is called irreducible initial water saturation. Probably most of you already took such kind of course. You know what is the initial water saturation, right? Let's review how we get a sedimentary rock. So you have this deposit area, and then some sand moving in, is some sand bring in, right? You have sand bring in here. So this sand is going to deposit. Okay, this area initially, there's like for example, is a lake or river, whatever. You have a lot of you have water there. Then you have sand deposited in the lake. So then you form such kind of solid, right? So now you can understand. Then initially this water will stay with sand, right? So this water stay with water. So in other words, this pore is fully saturated. Fully saturated by water. Okay. So then how could we have oil reservoir, for example? And then oil migrated here. So when the oil migrated here, what happened? It's going to drive some originally water away from this pores, right? Because for oil to come here, some water must be driven out. So this oil is occupied original pores were occupied the pore volume originally occupied by water. Then the question is, can the oil drive all the oil out? No, because you see, from by our experience, we know that it's kind of water where any fluid, like water or oil, will try to stick to the rock, right? So you cannot 100%, you could drive some water in the pore volume, pore space, but some water will stick to the rock surface. So it's kind of like a water film stick to rock surface. So which oil cannot drive this water out. So therefore, after oil moving here, we still have oil there. We call this is called initial oil, or I mean, still have water there. We call this one is initial water. So that is called initial water saturation. All right. By the way, I did not mention water saturation. Let me simply add it. What is saturation called? Let's say water saturation. Water saturation is water volume divided by total pore volume. Okay. So in other words, saturation represents a fraction of water volume, a fraction of total pore volume. All right. So now you understand the initial water saturation. What we have observed, sometimes because this water cannot be driven out by oil, right? So therefore we call this initial water saturation irreducible initial water saturation. And we found, and in some cases, irreducible initial water saturation in shale reservoir is extremely low. Extremely low. We call the sub. Sub means below, right? Extremely low initial water saturation compared to the initial water saturation in a conventional reservoir. All right. So then the question is, why in shale reservoirs sometimes this initial water saturation is extremely low or very low, even lower than conventional irreducible water saturation of sand pad or sand rock. This is, we need to recall how we get sometimes, let me explain how sometimes, well, let's come explain to how shale were formed. Now, in this picture, it is regular or conventional. Let's use conventional. Talk about we say the shale is unconventional. Let's say this is a conventional. Okay, so this is a conventional rock, but in shale, sometimes, like shale, how come we have shale here? This is shale. Initially, you have some kind of, like for example, is organic materials. And like trees. That's easy to understand. Let's use a trees example. It's trees there. It's deposited here. organic materials. There's no oil yet. Okay. So later on, so now you have, then later on have some sand is packed. So we have some sand. Okay. So later on, some more oil come here, like all conventional rocks. Then what about the original? You have organic materials, right? Organic materials during the deposit for a million years. Okay. Then this part temperature is very high because it's have deposited and deep. Is close to the close to the inside, deep in the earth. The temperature is high. When temperature is high, what happens about these organic materials? So organic materials will form, organic materials will become oil by extremely high temperature. Okay. So then initially you have some sand here, you have some, then how could sand was brought here? By water, right? Okay. So now you have water, but then when the temperature is high, when the temperature becomes higher, so what about water? Water initially liquid could become a vapor, right? Okay. When the water becomes vapor, what happens? It's easier to escape from this area, right? Because vapor is lighter, and by gravity, or if you have some external forces or somehow, so it's easier for vapor to escape from this area. Then let's think about it. Then is because of some water escape. So what about this then? This water saturation will become low, right? So therefore, that's why in some shear rocks, and the water saturation could be lower than the irreducible water saturation. Irreducible, that means by simple pressure displacement, water cannot be displaced further anymore. But sub-irreducible water saturation, that means even for this irreducible water saturation, because of vaporization, water even less. Okay. Now you understand what is called, why we could have irreducible water saturation. All right. Next one, I'm going to talk about let's see. Let me more parameters about shear rocks. Before that, let me check what is our class schedule. I try to follow this class schedule. From this is a 9 up to 9:50. So about okay, 10 o'clock. Wow. 10 o'clock plus 11. Okay. Somehow it's not right. So we first lecture is today should be the, no, wait a minute. Today we started from, let me check this one. We have time difference. I need to figure out this one. So today we're starting from 9 o'clock. Yeah, okay. Starting from 9 o'clock, first class should be about 10. So your 10 o'clock, and to me it should be 11:30. Okay, I just mark it for 11:30. 11:20. All right, so we have enough time. Let me continue then. All right. Now let's continue. So next parameter I'm going to explain is and kerogen. So what is kerogen? Kerogen is naturally occurring solid, insoluble organic matter. Now, earlier we mentioned several times organic matter, right? Now here is organic matter, now here. So what is kerogen now? It's actually is organic matter that occurs in source rock and can be yielded upon heating. I just explained, right? By the high temperature heating, and then this organic materials becomes oil or gas or natural gas. Okay, so then typical organic constitutes of the kerogen are algae and woody material. That's why earlier I say I use trees. That's how it's easy for we see trees, right? So I simply use a tree to represent woody materials or organic materials. So basically, kerogen is a solid. Okay, so it's a compressed trees. But you can understand like this way, or compressed, or by high pressure or compressed. This organic woody or organic materials compressed by a very high pressure, it will become solid, right? So that is solid organic materials. It's called kerogen. So first, what is that? You understand what is the kerogen, and next one is next one is thermal maturity. So what is the thermal maturity? So degree of heating, thermal maturity. Thermal is heat, right? So what is maturity? Means degree of heating. Okay, so is the degree of heating of a source rock in a process of transforming kerogen into hydrocarbon. So it's a heating process. Okay, thermal maturity is commonly used to measure virginity reflectance or by pyrolysis. So how to measure this maturities? We can easily understand, right? What is the thermal maturity? It comes thermal is heating, maturity, how much this kerogen is heated. Yeah. So then this kind of explanation, but how do we use parameter to describe such kind of thermal maturity? All right. So first one, we use called a vitrinite. So what is called vitrinite then? Vitrinite, this is first it was called a vitrinite. So let's look at this woody material, kerogen material. Such kind of materials generally composition is kind of uniform, and we under the heating see how this vitrinite changes. Okay, and so we use this. So in other words, what is the vitrinite then? Its reflectance is measurement of source rock maturity. So it's kind of how to measure such kind of vitrinite then? We use such kind of light cast on its light and cast on this rock and measure how much light reflected back. So probably we do not need to really describe how to vitrinite. Simply says we use vitrinite to describe maturity. What is the vitrinite? We do not really, it's kind of these geology terms. We do not have to worry about too much. So in other words, basically we use, what we do need to know is, if the thermal maturity is high, that means more heating, right? Thermal maturity talk about degree of heating, right? More heating, then vitrinite, this parameter is higher. How to describe this parameter? We use percentage reflectance in the oil. So we talk about our cast some light and see how much light reflected, right? So this percentage, typically we use called the R percentage. Okay, so basically it was a percentage. Now it's kind of not clear, right? Let me simply just use some numbers to describe such kind of thermal maturity. Thermal maturity, first, we use symbol RO. First, we use RO to, basically we use RO to describe such kind of thermal maturity. The symbol RO. Looks like any license. Okay. Okay. Now we talk about first symbol use RO to describe thermal maturity. And I also mentioned use percentage, right? Let's see what is it. So we get some idea what the percentage means here. Let's say if the percentage is 0.6, okay, it is generally is onstart of oil generation. So in other words, if the heating degree is below this 0.6%, 6% O, then we do not have oil generated. In other words, this kerosene is still a solid organic matter. And then as we increase, it's easy to understand now, as we increase heating, then we're starting to see oil. When the RO reaches 0.9, and we have a lot of oil generated, then we're further heating. If we're further heating, then some generated oil will vaporize, right? Will become a gas, right? So now when we're above this 0.9, and for example, about 1%, we're starting to see some gas coming out. And then, of course, then we use further heating, we get more gas. Then we're starting to see the dry gas. Then it's further, about 2%, we completed dry gas. That means all the oil is converted to gas. Now you can get some sense, right? So that's so as the thermal maturity, as the kerosene is further heated, and we starting get an oil, and then starting get gas, and then get a pure gas. Okay, so that's what I need to know. Okay, so therefore, this is the way generally we use our. Here we just use one example, vitrinite, such kind of parameter to describe maturity. We could have other methods to describe maturity, right? So then in shear terms, when we're dealing with shear reservoirs, even you could have other parameters to describe thermal maturity. For comparison reason, we always convert to RO. So generally, we always use RO to describe thermal maturity. And say you can easily to understand as RO is very high, then we could start to see some not only natural gas or hydrocarbon gas, we could also have nitrogen or even H2S or CO2. Okay. So in other words, you have different gases will come out when the heat is very high. All right, so that is thermal maturity. And then so then the next question is, we need a thermal maturity is high or low is better? High or low is better? Let's say from this, let me use a daily life experience to explain this concept. Now, in the morning when you eat bread, sometimes you use what's called a toaster, right? Bread toast to toast this bread. So now in the beginning, is bread is kind of soft. Sometimes if you eat, it's kind of stick to your teeth, right? But if you toast, it's kind of crispy, right? You like it, right? So therefore, we sometimes, especially in the morning, if you have time, you always toast for bread. So now if it's light, then but sometimes you are in the morning, you are rush or something. So you toast sometime now it's some, so bread turns to brown. But because you rush something, you forget to turn off, then what happens? The bread turns black or overcooked. So now from your daily life experience or from this picture, which one do you like? So obviously if the overcooked, this is brown, it's like black, right? So you do not like it. So you know what the best is, you must be right degree of heating, right? So therefore you choose the best of it. This is brown. This is not enough cooked. So therefore, from this picture, similar to the thermal maturity of the shale reservoirs, shale rocks, and we need inter-optimum or intermediate heating degree, thermal maturity, into intermediate maturity. Okay, that's very important. So in other words, we need an optimum or intermediate thermal maturity. Let's go back to previous slide. What is intermediate maturity? So it's about 0.9%. This is for example, but not exactly. You know, different rocks you have different optimum maturity. It's about 1% or 0.9%. Okay, but not fixed value. So, but basically, is your ideal is we need an intermediate thermal maturity to get the best value of organic chelagen. Okay. Now let me further explain a little bit. Last one is called total organic carbon. What is organic carbon? Carbon, so oil gas is hydrocarbon, right? Hydrocarbons. So then easy to understand is for us to get more is higher carbon content is better, right? So therefore, let's look at this picture, see here. This is total organic carbon. So in other words, what is total organic carbon? And okay, what about that? We stop here. It's over time. We stop here and get a break. You can go to a washroom, get some water, get a drink, something. We come back in 10 minutes, or let's say, now it's about, so let's about give you about 10 minutes. So far, about almost close to your time is 10 o'clock. So let's come back to about 10:05, okay? Come back about 10:05. Thank you.
Okay, thank you. We'll come back at 10:05, right?
Okay, I'm sorry. Let's, by the way, maybe let's feedback. Is it too slow? So speed is okay or too slow, too fast for the content?
So it is okay. It is okay.
It's okay?
Yes, yes.
Okay. Did we continue? Yeah. Okay.
Yes, yes, yes. Sir.
Yeah, let's so you can see you can see it, right? It's on my screen, right? Next, we're going to talk about total organic carbon. As I mentioned, so oil gas is carbon, right? So then this organic carbon means simply how much carbon contents in the rock. So that is, so from the name we can understand, we can understand what is the meaning, right? So formal definition is the concentration of organic materials in source rocks as represented by the weight percentage of organic carbon. So this is basically what is the weight percentage in the solid in the rock. So then is how to measure it, how to describe it, how to present it. So use for example, if the 1 gram of rock you crushed it and then you burn it. So then you're going to burn. Then because inside there is carbon, right? Then this carbon will be burned. After burn, it becomes CO or CO2. That's we know because if you're burning any like material, organic material like trees, we're going to have CO or CO2, right? So then after CO2 is gone, so then initially 1 gram weight will be lower than 1 gram. Let's say, for example, let me use an example here. Initially 1 gram of rock. After burn, some carbon is burned out and released, then only sand is left, right? Sand left, let's say, is 0.9 gram. So then how much carbon has been burned? So it's 0.1, right? 0.1 grams of carbon. So then what is the total organic carbon then? The total organic carbon, TOC, is simply just use this 0.1 gram, this carbon weight divided by total 1 gram. So now we get 10%. So in this example, TOC is 10%. All right, so that is example. Let's further look at, we talk about a thermal maturity. We need an optimum thermal maturity, right? Let's look at what is kind of TOC we need. So this left column, TOC is 0.5 to 12, greater than 12%. Then collagen quality, we rank it from very poor field to excellent. So now it is consistent with our common sense. As the TOC is higher, then we have more carbon in the collagen or in the solid rock. Then we have better collagen or get a better quality of organic matter, right? So therefore, that is so it's easy to understand. Okay, so then basically now I finished and introduced some important parameters or characteristics of shale rocks. So next one, I'm going to, let's see, share is starting. Let me do that. Let me share another one. All right. Now, next one is going to use some kind of numbers to get some idea what we have learned. First, I will need to get some, let me give you some kind of numerical values to explain further about permeability. So this slide you saw earlier basically described the Darcy experiment. I explained what is the permeability, right? So permeability is the ability of fluid to flow through rock. So far, like this example, we use this single phase fluid, for example, water. Okay. So far, we're dealing with a single fluid, and this permeability we call absolute permeability, right? Now let's use some numbers here. In this example, rate we use the water viscosity is 1 centipoints, and the rate is 0.5 cubic centimeters per second, and delta P is 2 atmospheric pressure. And let's calculate using Darcy equation to calculate what is the permeability value. Now, Darcy equation, we change Darcy equation in this form. So Q is 0.5, mu 1 centipoint, L here is 3 centimeters, A is 2 square centimeters squared, and delta P is 2 atmospheric pressure. Now, measure here, we use this Darcy unit system. So you need to know. So then you could from this Darcy equation, you could use this form. Every parameter is in SI unit, or every parameter is in Darcy unit system. If you use these two unit system, you do not need any unit conversion factor. Okay, so in this Darcy unit system, just to keep in mind, this is the cubic centimeters. Viscosity is centipoints, and delta L centimeters, delta P or phi potential, or is atmospheric pressure, areas centimeter squared. If you use this unit, calculated value is called Darcy. Okay, so in this example, we calculate use water. We calculated the permeability for this rock sample is 0.375 Darcy. Okay, then let's move on. Use another one. We could use oil, right? Let's say if we use oil to do such kind of experiment using the same rock, let's say what kind of permeability we measure. So oil we found is Q, oil viscosity is 3 centipoints, delta P is 2 atmospheric pressure. Then follow this equation and we use the same consistent unit system. What we found is 0.376, which is very close to what we got for using when we used water. So then from these two examples, what do you say? It does not matter we use oil or water to measure the probability for the same rock sample is same. So what does it mean then? In other words, so probability is rock characteristics or is a rock property. Okay, so it does not independent on the fluid used. So in other words, the probability is rock property. Right? It makes sense. So okay, keep in mind. Let's say All right, so what do you see here? Here is what do we have observed? Permeability for using oil and water is same. So K is same and K, okay, so now later I did not talk about gas permeability yet. So just first let's leave it. We're not talking about this yet. No, okay. Let's move further. Now let's move further. Give an example, another example. In this example, we are flowing both oil and water. Okay. So what I mean? So now instead of flow one, instead of using one fluid, we use two fluids, oil, water, flow simultaneously. So now we have oil and water. Their rate is water is 0.3, oil is 0.01, and we have water viscosity, oil viscosity. And the pressure drop, we still use 2 atmospheric pressure. Let's using this now, then let's go back to this Darcy equation. Let's first use the data for water flow. So then we calculate the PW is the permeability when the water is used. Okay, so then this use the water is 0.3, rate, viscosity is 1, and delta L is 3 centimeters, A is 2 centimeters squared, delta phi P or delta P is 2 atmospheric pressure. So now we get a 0.225. So then similarly, we can use oil. So oil, we have Q oil is 0.01. Oil viscosity is 3, delta L, 3, delta A, or A is 2, delta P, delta phi, or delta phi is 2 atmospheric. We now we get a 0.023. Okay, so first, what a problem? Now, when the two fluids flow simultaneously, if we use water data, we get a 0.225. But if we use oil, is 0.023. So almost the key oil, almost 10 times lower than key using water. So that is, then the question is which was correct? Because we mentioned earlier, permeability is rock's property, right? So it should, and we mentioned it should not depend on the fluid used. But now we found it does depend. Okay, so it does depend. So what is the problem? Why we in this case they are not the same? Okay, how to explain it? So now because you have two fluid flowing. Now two fluid flowing. Earlier I mentioned pour is like that, right? We have this called pour solute, right? If you have pour solute, if the water, for example, if you have oil block this pour solute, so then water cannot flow out anymore. Let's say if you have water coming to this pour, then water cannot flow through pour anymore. So not, but your water, you still have water saturation still. So that is partially explained when the two fluids flow at the same time, the flow of water will be affected by existence of oil. So similarly, then if you just change it to water, and then oil is going to be stopped by water. So in other words, the oil flow will be affected by existence of water. So therefore, they have interactions. So because of these fluids interactions, now you use different fluid data, you will get different probability. Okay, that is so that is easy. Okay, looks like it can be understood, right? Let me give you a daily life experience. For example, now we are in the same classroom. If everyone flow, like in case of emergency, we want to rush out. Like say in case of emergency, we try to get an escape from this classroom. What do we do? Ideally, we need to one by one quickly organize escape from classroom, right? If the classroom is in disorder and everybody try to escape at the same time, what happened? The more people is going to block the door out, right? So therefore, that if everybody try to get out at the same time, then even worse, it's more difficult for for us to get out. So therefore you have interaction jammed. We influence, we affect each other. So therefore we could not have effective escape. Right? So similarly to this case. Okay, that's the first phenomenon. So now we have a fluid interaction problem. And what do we see? Another one is, let's add oil probability, water probability together. So 0.225 plus 0.2023, now we get a 0.248. So now even we add two probability together, it is still lower than absolute probability we got earlier when we used single phase fluid. The reason as I explained, because there's such kind of interaction between fluids or actions. So then the flow is not effective, is less effective. So therefore the probability is lower than single phase flow probability. All right. That is phenomenal. And because of this phenomenal, let's introduce some terms or concepts. First, this KO we call effective oil probability. Okay. This KW we call effective water probability. And then this effective oil probability divided by absolute probability, we call this 0.06 is oil relative probability. Now we introduce another term called relative probability. And then this is a relative water relative probability. So then it's important to notice that PRO plus KRW is less than 1, which is similar to the oil effective probability plus water effective probability less than absolute probability. So that is very important characteristics of relative probability. So in other words, when you have multi-phase flow, your flow is less effective. Okay, so that's a definition here. Relative definition, formal definition, effective probability, and the relative probability. All right, so that is relative probability. Now, how does it look like? Now, this look like this one. Say, look, so here is the relative probability. Here is the water saturation. And first, let me explain what is the relative probability, how relative probability changes water saturation. Saturation is, well, I say this is water saturation, right? If the water saturation is high, that means more water is flowing. So then what is about water relative probability? That should be common sense, right? If you have more water flowing, then water relative probability or water effective probability should be higher. So therefore, we have this curve. Okay, so this curve is KRW. So in other words, KRW increases as SW increases. Okay, now if the SW increase from left to right, then oil saturation is going to reduce, right? Because oil saturation plus water saturation should be equal to total saturation, which is 1. So then this is oil saturation is 1 minus SW. Therefore is the oil saturation reduced direction, then it's easy to understand oil relative probability is going down. So therefore we have such kind of KRW and KRO curve. And this one, now in the middle, this purple one, dark purple one, we have this is KRO plus KRW add together. It's called total relative probability. This is called total relative probability. So now you can see total relative probability at any saturation always lower than 1. Okay, so this slide shows the characteristics of relative probability in general term. Now, about this course, we talk about shale reservoir, right? Now, then you may have question, how's shale relative probability look like? Now let's move to next one. Let's first look at this. This is what is this one we just said? This is PRO, right? What of this one? This is KRW because here is water saturation. So water saturation is higher, KRW is higher. So that is conventional rock or regular relative probability curve look like. Okay. And then another thing, let me go back to this slide. Another thing I forgot to mention is, let's look at here, this saturation. Now, when the water saturation from 0 to 0.2, when the water saturation is very low, so then look at it, for example, let's look at this pole here. Let's look at a pole system here. Now, this is water, and here you have another water, because water saturation is very low, right? So then in the rock, these two water are not connected. So then water, if they're not connected, water cannot flow, right? Because it's not connected. So therefore, when the water saturation is low, then KRW water is 0. Here is 0. The water cannot flow. So your water saturation must have a minimum saturation, in this case, 0.2. Then you see water starting to connect to each other. So then if you have pressure drop, then water can flow. So this water saturation is called coordinated water saturation, or the term actually earlier we used what are called initial water, it's called earlier we use irreducible, right? Irreducible water saturation. Okay. We call it irreducible water saturation. But then if it's greater than this minimum saturation, so the water starting to flow or can be reduced, right? Or can flow. So this one is called reducible water saturation. We just choose in here, this side less than 1, this is irreducible. But this side is reducible. Okay? Or sometimes maybe you heard another name called coordinated water saturation. or mobile saturation. Mobile or reducible, similar meaning, right? So this is water saturation. In other words, this you have minimum small water saturation. Below this saturation, water cannot flow. Okay, similarly in the right-hand side. Now, when the water saturation high is from 0.1 to 1, 0.8 to 1, then oil saturation will be 0.2 to 0, right? So now in this region, oil saturation is very low. It's easy to understand. If the oil saturation is very low, oil cannot flow either, because oil saturation too low, so oil phase, they're not connected each other, they're not connected, so flow cannot flow, oil cannot flow. So then this one, we generally call what's called residual oil saturation. Why we call it residual? Because in generally, when we're dealing with the oil reservoir, initially oil saturation is high. Then we'll produce oil, right? Until oil saturation is such kind of very low area, we cannot reduce anymore. So this oil, small oil saturation, will remain in the reservoir. Therefore, we call the residual or remaining oil saturation, or it's called residual, because it's still remaining in the reservoir, but it cannot flow anymore. So therefore, we have a residual oil saturation. Okay. Now, this is a very important concept. Now, let's come back to this relative permeability curves again. Now, here you have, here is SW. This is KRO, KRW. Here is HWC. It's a mobile or continuous water saturation. Here is the residual oil saturation. It's kind of in between about 10% or 20%, 10%, 20% range, right? From this picture, you can see that. Now, let's look at this is the ordinary traditional reservoir rock. In the right-hand side, let's look at low permeability reservoir rock, like shale. How this relative permeability look like? What we found is, looks like, and this is a case. Actually, we use use gas and water case instead of using oil. So here we use gas, okay? Because in shale reservoir, especially in the early days, when we talk about shale reservoir, we generally talk about shale gas. Okay, so this work was done about a shale gas reservoir. So we use the water and the gas. Basically, we use the gas to replace oil, okay? So what we found out is, here is residual HWC is what is calling the water saturation, right? So what do we found? Calling the water saturation here. What is that? Here is 50%. Here is about 80%. Below this 80%, what do you see? This is KRW. Here's here. This is KRW, right? No, below 80%, KRW is 0. In other words, what does it mean? In shale reservoirs, water cannot flow sometimes. I mentioned sometimes, not always. Sometimes water saturation could be as high as 80%. Water cannot flow. Why? Okay, so that is one characteristics of shale relative permeability for water. Why? Because remember, shale pores are very small, right? If the pore is very small, you think about a water film is going to coat it on, water film will coat rock grains, right? Or water film will stick to the rock surfaces. So then, if let me explain it this way. Let me use some. I need to add something. Let's say, typically, let's say if you have such kind of pore, let me use enlarged pore. Here represent the pore. Okay, here's like water. Okay. It's easy to understand. Water will flow easier in the middle of the pore, right? But in the near the rock surfaces, this area, water can barely flow because this water film stick to rock surfaces. Make sense? So there's special theory. I'm not going to cover this one, which should be discussed in the rock properties. But I cannot spend too much time. I just simply use schematic to explain to you. All right. You think about it. If this pore is very small, then relatively this water film will become very thick, right? So therefore, you have more water saturation or more water, more pore volume, more portion of pore volume will make water not able to flow. Clear? So therefore, that's why this in shale reservoir, this current water saturation current water saturation is generally higher than the current water saturation for traditional or conventional reservoir rock. Sometimes it could be high as 80%. And then similarly, for the gas, now gas, let's say gas is by this part of this gas saturation, right? Now gas, this saturation is close to 50%. So then when during this region, when the gas saturation is below 50%, the gas saturation almost zero, similar to water. In other words, because the shale pore is very small, so even some highest gas saturation cannot flow either because its gas absorbs on rock surfaces. Absorb or stick, you use a common word is stick to rock surfaces. So therefore, some portion of the gas cannot flow, or some of the pore volume cannot be used for gas flow. So therefore, for very interesting thing is, let's look at it here in the middle part. Let's in this middle part. Okay, let's say in this middle part. Now this middle part, either KRW or KRG is zero. That means within this region, when the saturation, water and the saturation of gas are in the intermediate region, either of them can flow. Either of them cannot flow. So none of them cannot flow. None of them can flow. Okay. So this region is called something special name called permeable gel. Okay. Gel means you cannot move, right? So it's called permeable gel. So in other words, in shale reservoirs, you have such kind of permeable shale phenomenon. Okay. This phenomenon. Okay, next two slides basically about capillary pressure. I have not mentioned, I'm going to explain later on because I have not introduced capillary pressure yet. All right. Now, next one, let me introduce another concept. Now ask them to introduce let's first look at this picture, beautiful pictures. All right, let's look at this beautiful picture. Here is a flower, and here's droplet. Below, bottom, these three droplets are water droplets. Okay, you probably you did not know this, or you can understand. During the rain, when it rains, what do you see? You see some water droplet below the leaves or below the flowers, right? Then why? So we know we have gravity, and why this water does not drop? Why this water droplet does not drop? Even you have gravity to pull this droplet down. Then if it does not drop, there must have another force pulling it. Okay? So therefore, you must have another force pulling this water droplets. Then what is this force? Okay, let's look at here. Now, there's this water phase. Here you have flower. In between, you have interface, right? So in other words, there must exist another force at the interface. Because based on our analysis, there must exist another force at the interface. This force is called interface force. Right? Interface force. So typically we use an abbreviation called IFT. Or I'm sorry. Okay, let's interface force. Interface force, and we have special term called this interface force tension. And then we use special term called IFT. That's called interfacial tension force, interfacial force. Instead of using force, we use special term called tension. So therefore, we have special term called interfacial tension, or IFT. Okay? So then you may question, how could you have interfacial tension? Why do you have interfacial tension? Now let's look at this example. Let's look at this schematic. In this schematic, and this is it's like a bar. It's like a cup. In the cup, you have water. Okay, here is air, right? But now let's look at analyze one water droplet inside of water. Now, inside of water, as you know, between water molecules, there's a universal force, right? So this is from college in physics. Between any materials, any molecules, or any large or small, any objects, there exists some kind of universal force. This universal force could be attractive force or repulsive force. Okay, but they in equilibrium. So therefore, when they are in equilibrium, they do not move. So this water droplet does not move, right? So therefore, you have a repelling force, attraction force, this is universal force. And this universal force at every direction is same. What is universal force? Universal force is proportional to what? Materials, when mass of materials or masses of two materials or two objects, and proportion to this mass. In other words, if the molecule is large, this force between them will be larger. So now here you have molecule, water molecule, water molecule, water molecule. At every direction, water molecule is same, right? So therefore, mass is same, M1 equal M2. in every direction. So therefore, this forces in every direction same. So therefore, the in equilibrium, water does not move. So it's in static. Now let's look at the interface. Let's look at the interface. At the interface, here is smaller air molecules. Air molecule is smaller, right? Let's use smaller one. Let's use smaller. Now let's look at just look at one molecule smaller. This is water. This is air. Now, what about this force here? Here you have water, but here you have water and air. Now, this air is smaller. So what about the force? Force will be smaller too, right? So therefore, then this force F1, this force F2, and the F1 is smaller than F2. F1 is smaller than F2. All right, so then if it's smaller, then you have this force, you're going to pull this water molecule is going to go in this direction, right? Go to the water. This surface water molecule will go to the water phase. But in reality cannot, because why? Because you have other material, is going to have another repelling force, it's going to stop the water coming in. So you have you generate another repulsive force to push this molecule up. So now you have this actual force now. This actual force can only exist at the interface. So therefore we call this force is interfacial force or interfacial tension, or RFT. So now we understand why at interface we have special force, which is interfacial tension, which is going to push this molecule up to prevent it further come to the inside of water phase. Okay, inside of this water phase. Then go back to this picture, then this why water drops does not fall, because you have actual force push or pull this water droplet up. All right, so now so far you understand why we have interfacial tension. Okay. So now let's further make formally define interfacial tension. Interfacial tension abbreviation is IFT. Sometimes we commonly use the sigma to describe it. It's could be this interfacial tension could be existing at any interface. Could be liquid, gas, liquid, solid, and okay. Like say for this a typical value, the water oil interfacial tension is about 25 millinewton per meter. Okay, look at this unit. It's meter per meter. So in other words, what is this tension? Why do not use force? What is this? We instead using tension term. This tension term means unit is per meter. In other words, this force, interfacial force, is proportion to length. That's easy to understand. Let's go back. If this interface is longer, your force will be longer, right? So therefore, this force is longer as the interface is longer, but interfacial tension is not. So therefore, it is this tension is better parameter to describe such kind of interfacial force. It is per meter. Okay, this is the typical value is 25 for oil water. Okay, we stopped here today, and we'll continue tomorrow. Okay. Thank you very much for you. And by the way, If you have some suggestion to improve my teaching, or whether it's too difficult, or maybe I explain too much details, or less, or no, maybe not enough details, and let Professor Mandel knows, so that I could try to improve in the next sections. Okay. Thank you, and have a good day.
Thank you, sir. Thank you so much, sir. That was a very interesting explanation and lecture. I'm sure everyone thoroughly enjoyed it. We'll see you tomorrow again. And for all our participants, the next segment will start from 11 a.m. Thank you so much, sir. See you tomorrow.
Okay, thank you. Bye-bye.
Bye-bye.